Hi guys, welcome to the channel. So in the previous video we were discussing about the absorption laws and we were trying to discuss the two laws. The first law was the Lambert's law and the second law was the Beer's law. We have already discussed that what is there in the Lambert's law. So we have discussed this part, right? Also we have derived the expression for the Lambert's law. Now moving ahead to the Beer's law. So just like Lambert's law, the initial statement for Beer's law will remain the same. So we will write it down. So it states that when a beam of monochromatic light is passed through a solution of an absorbing substance, the rate of decrease of intensity of radiation with the thickness of absorbing solution is proportional to So till now the statement is similar to the statement of Lambert's law, but from now this will change. It will be proportional to the concentration of solution. So this is what is Beer's law. So in this law, the rate of decrease of intensity with respect to the thickness will be proportional to the concentration of solution, that is C. So this will be the Beer's law. So if we want to combine the Lambert's law and the Beer's law, so what we will get is minus di by dx, that is rate of decrease of intensity with respect to thickness, that will be proportional to intensity and the concentration, right? So combining these two laws we get this one. Now if I want to remove this proportionality sign, I have to introduce one constant. So this time the constant will be k dash because we have already used the constant k. So minus of di by dx will be equal to k dash into I into c, right? So this will be the expression. Now I will take this negative sign to the right hand side and dx to the right hand side, and I will take this I to the left hand side. So we will get di upon I equals to k dash minus of k dash into c into dx. So this is simple rearrangement. Now from here, just like the case of Lambert's law, we will get I is equals to I naught e to the power minus k dash c x. We need not solve this again. We have solved this type of expression in the Lambert's law. So we will directly write this part. So now combining the two expressions of Lambert's law and Beer's law, what we have got is I will be equal to I naught e to the power minus k dash cx, and also one more expression, that is log of I naught upon I will be equal to epsilon into C into L. Now what are these? We will explain. So this is a very important expression. So now we will define one by one what are these terms. So I naught will be the intensity of incident light. Now what will be the incident light? Suppose this is the cuvette in which we have the solution. So the light which will be initially incident, that will be I naught, right? After this, I, that will be the intensity of transmitted light. So when this incident light goes through the solution, some part will be absorbed and the remaining part will be transmitted. So the part which is transmitted after this absorption process, that will be the transmitted light, that will be I. Now next, C, that will be the concentration of solution. Now what will be its units? That will be mole per liter. Next is small l. L is the path length, and generally talking about the path length, that is generally 1 centimeter. That will be for the cuvette, this path length. That will be generally 1 centimeter. So this is small l. Now moving ahead, epsilon. This is molar extinction coefficient, or you can say the molar absorptivity. And one last thing, this overall expression, that is epsilon into C into L, that is also called as absorbance A. So we can write it as like this. So here A will be the absorbance. So this is all about Lambert-Beers law. Now this law has certain limitations. So now we will discuss the limitation of Lambert-Beers law. So there are certain limitations to Lambert-Beers law. So this law is not obeyed when we have different forms of absorbing molecules in equilibrium. For example, we have keto-enol tautomerization. That is, what happens in this case, we have one absorbing molecule and two different forms of that molecule, that is one keto form and one enol form. These two forms, they are in equilibrium with each other. In that case, Lambert-Beer law will not be applicable. So there should not be any tautomerism present. Now second is, this law will not be obeyed when we have fluorescent compounds. This is the second limitation. Third, if the solute and the solvent which is there, see, if we have a solution, then it will be comprised of solute and solvent. Solvent will be of higher amount and solute will be of lower amount. For example, if we have salt in water, then salt is the solute and water is the solvent. So if we have solute and solvent in a solution and they combine and they form complex with each other, in that case this law will not be applicable. That is, if we have solute and solvent in the solution, then there should be no any sort of association between these two. There should be no association between solute and solvent, and they should not be forming any type of complex after their association process. If there is the case, of complex formation of there is some sort of association between solute and solvent, in that case Lambert-Beer law will not be applicable. So these are some of the conditions, these are some of the limitations of Lambert-Beer's law where this law is never obeyed. So now with this, moving on to the next part, that is the main basic theory of the UV, or you can say the main basic principles on which the UV spectroscopy works. So we will discuss some basic parts of the UV. So moving on to the basic theory part of UV spectroscopy. So if we first talk about the range of UV. So range of UV is 200 to 800 nanometers, right? So this is the highest wavelength and this is the lowest wavelength. Now we all know one formula, E is equals to hc by lambda. So from here we know that E is inversely proportional to the wavelength. Here the wavelength is maximum, here the wavelength is minimum. If wavelength is maximum here, then here energy will be less, right? Lowest energy in case of UV visible, and here energy will be highest in case of UV visible. Now whenever we do the scanning in UV visible spectrophotometer, what happens, the scanning starts from lower wavelength all the way up till the scanning starts from higher wavelength until lower wavelength. Why this is so? Because we move from low energy towards the higher energy. So that is why whenever we do the scanning in the UV visible spectrophotometer, if we are doing the scanning from 200 to 800, if we want scanning of certain solution from 200 nanometer to 800 nanometer, then the scanning process will start from 800 and will go up till 200 nanometer, right? So why this is so, now you know, because the scanning process starts with lowest energy and move towards the highest energy. So this is the main reason. Now you know the range of UV visible, so roughly 200 to 800. If we talk about UV and visible range is separately, then 200 to 400 is the UV range, and from 400 to 800 is the visible range. Now after the scanning process, you will see that I have not made any sharp peaks here. Why? Because in UV spectroscopy we never get a sharp peak, we always get a broad peak, or you can say broad band, in case of scanning in UV visible spectrophotometer. Now this is also one of the most important questions, why we never get the sharp peaks in case of UV scan. So we will discuss that in a bit, but after this, moving on to the next part. So now moving on to all those important questions, we need some basic knowledge. So first we will discuss some basic parts and then we will try to answer those questions which are arising, that is why we get broad peak and why we do not get the sharp peaks. So suppose we have a certain molecule, for example, now suppose we have this molecule. In this molecule, if we look closely, we have a pi bond, and we also can see the lone pairs. So the molecule has sigma bonds, pi bonds, and lone pair as well. Now first we will consider the sigma bond. If we talk about the sigma bond, sorry for my drawing. If we talk about that, comparatively better now. So if we talk about the sigma bond, then this is like head-on overlap. So because of this head-on overlap, we have a strong bond, right? So it is a very strong bond. If we talk about sigma bond, it is very strong bond. Why? Due to this head-on overlap. If we talk about the pi bond, I'm saying sorry in advance for my drawing, so I'll try to make it. So this sort of overlapping, that is the sideways overlapping, this is kind of a pi bond. This is less strong as compared to the sigma bond. You can see here the overlapping is less, right? This is head on and this is sideways overlapping. So this is less strong as compared to the that sigma bond, right? So this is the pi bond. Now we will try to look at the energy levels. If we consider the sigma bonds, pi bonds, and also the lone pairs, right? The lone pairs which we have seen. So if we try to draw an energy level diagram, sort of energy levels, so sigma will be here, followed by pi, then we will be having non-bonding, then pi star, and then sigma star, right? These will be the energy levels. So you will see here the energy gap is highest between sigma and sigma star, right? This is why this is so, because sigma bond is very strong in nature. So here these sigma and pi, these levels, these are bonding orbitals. These, these are non-bonding, and these are anti-bonding orbitals, right? So till now I hope you know what are the energy levels. These are bonding, these are non-bonding, and these are anti-bonding, and what are their placements. Till now you know that sigma bond is strongest and followed by the pi bond. And now we will look on to the transitions. I was talking about sigma sigma star transition, but then I stopped. Why? Because I want to discuss that in a separate topic altogether, that is types of electronic transitions. We will discuss about the various types of transitions which are possible in between these energy levels shortly, maybe, or confirmed in the next video. So in the next video we will take the topic of types of electronic transitions. What are these transitions between these energy level, what is their theoretical and practical possibilities, and how about we will go to the various conclusions regarding the spectra of UV visible spectroscopy using this information of transitions in between these levels. So I hope until now everything is clear to you guys. So far that's it for this video. Thank you so much for watching.